This video follows on from one down here where I explain how to find prime factors of a number, and in this one I'm going to go over these examples and work through them so that you can check that you can actually do it. That means you have to have tried them yourself first. I dare say that when I do them, you can watch me do them and you can think, okay, yeah, I follow. Yes, that makes sense. Yes, I see what you're doing there. Which means that you can follow me to get to the destination. But can you get to the destination on your own? Because you're going to have to. Following me means you can understand it, but actually being able to do it yourself is what we're aiming for. So I want you to have tried those before I go through them. So if you haven't done that already, if you've just come to this video without having a look at the previous one, go and have a look at that one. If you haven't tried them yet, please pause at this point and write those down and have a go at finding the prime factors yourself. Then I'll go over them. Okay, I'm going to do these in two different ways. There is the factor tree method, which is possibly the simplest to understand, and then there's also the division method, which some people prefer because it's a little more logical and structured. So I'm going to sort of alternate between the methods. You'll see they're basically the same thing as I do this. They're all involved in just finding factors of each number and then finding factors of the factors, etc. It all comes out in the wash, and I'm hoping you're going to be able to understand, because understanding is paramount. Okay, we're going to start with 840. So that one I'll do using the factor tree method. So I'll put 840 up here. Okay, so I divide that into anything I like when we're doing factor trees. Obviously it divides by 10, so I'll do that. So I'll put 10 and 84. 10 and 84, okay. Well, let's do the 10. I think we can get that one out of the way. 10 is 2 times 5. And as you can see, 2 and 5 are both prime numbers. So those two are actually prime factors. So I can put a circle around those, and those two, therefore, are sorted. Now I have to work out the factors of 84. So what can we do? We can divide that by quite a few things, can't we? Well, what should we divide it by? Let's divide it perhaps by 4. So how many 4s are there in 84? 21. Okay. 4 and 21. Could I divide it any way I like? As I said in the previous video, it doesn't matter how you actually do this, what numbers you pick as your factors, because there is only one set of prime factors for any number. So whatever method you use to do this, however you tackle it, however you actually find your way through, the numbers you end up with will always be the same, assuming you've done it correctly. So it doesn't actually matter what numbers I choose. I could divide it by whatever goes into it, not a problem. Okay, I could have done 7 12s. It doesn't matter. Okay, so 4 and 21 are not themselves prime numbers, so I can split those down a bit further. So let's see what we can do with 4. As I'm sure you know, 2 2s are 4. Not exactly rocket science. And 2 is a prime number. So if I put 2 here and 2 here, I've done the 4. 2, therefore, is going to be a prime factor, as is that one. Left hand. Right, so 21, we can split that one down as well. And that is 3 7s, and 3 and 7 are prime numbers. So we found 2 more prime factors. Now we come to the stage where everything we've got has been reduced to prime factors. And as I say, I must stress this, it doesn't matter what route you take through here, you're always going to end up with the same numbers. So we've got 2, 2, 2, 3, 5, 7. We need to express them in an ascending order. So therefore, collecting these up, we've got 2 times 2 times 2 times 3 times 5 times 7. Down there. You might want to cross them off as you write them out, if there are quite a lot of them, to make sure you don't forget any, or write any twice. 2 times 2 times 2 times 3 times 5 times 7. If you are asked to express that as powers, that would be 2 cubed times 3 times 5 times 7. Okay? Right, so that's that one done like that. The next one I'm going to do by the slightly different method where we divide by each prime number as we go. So let's put 120 up here. And let's divide that. Firstly, does 2 go into 120? Certainly it does. 60. And I divide that one. And what I do, of course, is I try 2 again. Does 2 go into 60? Yes, indeed it does. 30. Then we do 2 again, because we always start at the beginning with 2. Does 2 go into 30? Yes, it does. Okay. Does 2 go into 15? No, it doesn't. So we try the next prime number. Does 3 go into 15? Yes, it does. 3 5s. How you end that, because those obviously are prime numbers, how you end that depends on your matter of taste. You can leave the 5 down there. If you leave the 5 down there, I find that people quite often forget it. So I quite like to put the 5 here. What does 5 divide by? Just 5, because that's the smallest prime number that goes into 5. So then you've got them all down the side, and it means you don't forget any. So the answer to this one, therefore, is 2 times 2 times 2 times 3 times 5. Or, if you prefer, 2 cubed times 3 times 5, because 2 times 2 times 2 is, of course, 2 cubed. Right. That is the same as that. Seriously, that is the same as that. I've just set it out slightly differently and been a little more methodical in how I did it, by always dividing by 2, or whatever is the smallest prime number that happens to go into it. Whereas with this one, you just randomly find factors until you can't do any more, and what you end up with will be prime numbers. So that's a little neater and a little more methodical, but it doesn't matter. Use that if you prefer. I'll do that one for the next one. Okay. Next one then, I seem to have 495, doesn't it? Okay, so 495. Put it up here. Oh dear, what goes into 495? Does anything go into 495? 2 obviously doesn't. Let's see if I can divide it by 3. 9, 10, 12, 13, 14, yes. What I'm doing here in my brain is adding up the digits. If you add up the digits, 4 plus 9 plus 5, I get 18. And 18, I know, is divisible by 3, because it's an obvious number in the 3 times table. If that is the case, if the sum of the digits divides by 3, then you know that the number divides by 3. That's one of the little tricks, and there are several, I must do a video on that, to be able to tell whether certain numbers are divisible by other numbers. And in this case, we know it's divisible by 3. Okay, now I've got to do 495 divided by 3. So 480 is divisible by 160, so 165, I think. So let's have 3, and let's have 165. Okay, so 165, what can I divide that by? Well, it's got a 5 on the end. Must divide by 5 then, mustn't it? Oh, incidentally, 3 is a prime number, so I can put a circle around there. So I've got one prime factor already. So as I say, that divides by 5, okay? So 5's into 165. 5, of course, is a prime number, so that's a prime factor. How can I find how many 5s there are in that? Another little trick, if you double 165, you can then just divide by 10, and that is your answer. That's usually the easiest way of doing that. So 2 165s are going to be 330, so that is 33 5s. Okay. So I've got there 33. That is not a prime number. That divides, I suspect, by 3. So 33 is 11 times 3. 3 is a prime number, 11 is a prime number, so I've got my prime factors. Okay. For that one, so I can write those down here. So I start with the smallest, 3 times 3 times 5 times 11, or 3 squared times 5 times 11, if you want to express it like that. Okay. Right, that was 495. Let's try 64. Do 2's go into 64? Yes, they do. 32. Do 2's go into 32? Yes, they do. 16. Do 2's go into 16? Yes, they do. 8. Do 2's go into 8? Yes, they do. 4. Do 2's go into 4? Yes, they do. 2. 2 then is my final answer. 2, 2, 2, 2, 2, 2. Wow, that's a lot of 2's. So the prime factors of that are 2 times 2 times 2 times 2 times 2 times 2, or if you prefer, 2 to the 6. 1, 2, 3, 4, 5, 6. 2 to the 6th power is 64. That was a quick one. Lots of 2's. Okay. See, just when you thought this was going to be a really long, boring video. Right. Can't promise it won't be. Right, where do we get to? 64. 210. Let's do 210 by this method. It doesn't matter, you can use either method anytime, doesn't matter at all. Okay, 210. It divides by 10. There's a 0 on the end, so that's the easiest thing to do, isn't it? So let's have 21 times 10. Okay. 21, I know that's 3 7s, isn't it? So I'll put 3 times 7 over here. 10 is 5 times 2. So these numbers at the bottom are all prime numbers. So that was quite quick. We've got our prime factors. They've dropped out of that one quite fast. So putting these in ascending order, 2, 3, 5, 7. So we've got 2 times 3 times 5 times 7. Nothing more we can say about that one. Sorry, there's a butterfly in here now. Right. So if a butterfly flutters across, just pay no attention, just pretend it's not there. It's a tortoiseshell butterfly. It's rather nice. Anyway, moving on, where did I get to? Slight distraction. 297, right. Does that divide by 2? That's the first thing I'm going to do using this method. Does it divide by 2? No, it doesn't. It's an odd number. Does it divide by 3? I think it does. I think it's 3 times 99. So 3, 99. Does that divide by 2? No, it doesn't. It's an odd number. Does it divide by 3? I believe it does. I think 3 33s are 99. Okay, that one, again, that divides by 3. And it's 3 11s, isn't it? What does that divide by? 2, 3, 5, 7, 11. It's a prime number anyway. Okay. So, my prime factors of that are going to be 3 times 3 times 3 times 11. 3 times 3 times 3 times 11, or 3 cubed, which is 3 times 3 times 3, times 11. Okay. Rub both these off. For the last two then. 186. 186. Okay, what goes into 186? Well, 2 obviously goes into it. Because they add up, 8 and 6 is 14 minus 15. 3 goes into it. Let's do 2, it's probably easier. So we'll have 2. 2 goes 186 93 times. Okay. That, whoops, purple, is a prime number. 93, is that a prime number? No, it isn't. So 93, well, it isn't because they add up to 12, the digit, so it must be divisible by 3. 31 is a third of that, isn't it? So we've got 31 times 3. Okay. How about 31? That seems familiar. Yes, 31 is a prime number. So that is the finish of that one. 2, 31, 3. Okay, so we write those out as 2 times 3 times 31. One left, I'm hoping, unless I've missed any. 1,411. Okay, 1,411. Whatever I do with that, I've got to find the first factor of it. So, does 2 go into it? I think not. Does 3, 4, 5, 6, 7? No, the digits don't add up to a number divisible by 3, so 3 does not go into it. Does 5 go into it? Clearly not. Does 7 go into it? I believe it doesn't. Does 11 go into it? I don't think so. There's a way of finding out if 11 goes into things, which I sadly can't remember. I'll do that in another video. Okay, get out my phone as a calculator and try a few other things. And you can try each of these numbers, divide it into there and see if you get an integer answer. And keep on going through the primes until you find one that actually fits in exactly. You will find that 17 fits into it exactly, okay, and that the other factor is 83. So you will immediately find your two prime factors for that one, no matter which method you use, are 17 and 83. Okay. Now the only way of doing that is to go through the prime numbers until you find one that fits into it by constantly dividing using a calculator on paper, whatever, until you find one that fits exactly. Because that is the only way to work out the actual factors when you have a very large number, that's not very large, but when you have a larger number, which is the product of two primes. This is used, just a quick aside here, in cryptography, computer cryptography, when data has to be made secure so that it can't be intercepted and decrypted by other people. There's a system called public key cryptography, which is one of the many, many useful things that primes can actually do. And when you use public key cryptography, you use the fact that if you have two very large multiple digit primes, much, much bigger than these, very, very large primes, because of course there's an infinite number of primes, if you get two very, very large primes and multiply them together to make a very large number, it's very, very difficult, given the very large number, to work out what those two prime factors are when there are only two. If you have a large enough number, it can take a computer millions, billions of years of computer time to work out the two prime factors. And that is used in a system of public key cryptography, which is a very, very important computer use to keep data secure. You can publish the big, big number, and you can use that to encrypt, to encode the data, but you have to know the prime factors to be able to decode it. There's an algorithm for doing that. And of course you can't find the prime factors. So the public key is the big number, and the two factors are the private keys, which somebody else, obviously only needs one of them, can have. So there's a very important and very interesting field of computing cryptography known as public key cryptography using prime numbers. And that's a very, very important application of prime numbers. There are lots of interesting things about Mersenne primes and all sorts of stuff which you can find out about prime numbers. It really is quite an interesting topic.